Welcome to section 2.4 on complex numbers. In the previous section, we talked about how the square root of a negative number was not real. And this is because anytime I square a real number, that product is either positive or zero. We're now going to talk about imaginary numbers. Imaginary numbers are what are going to allow us to talk about the square root of a negative number. And to start off with, we're going to talk about the principal square root of negative 1. We're going to call the principal square root of negative 1 I. So I is going to be defined to equal the principal square root of negative 1, and it has the property that I squared equals negative 1. If a is a positive number, then negative a would be a negative number. And thanks to the number I, we can talk about the square roots of negative a. Those square roots would be I root a and negative I root a. Thanks to the property that I squared equals negative 1, if we square I root a or negative I root a, both would give us negative a. Now, when it comes to principal square roots, the I root a is going to be the principal square root of negative a. In other words, the principal square root of negative a will always equal I times the principal square root of a. Now, because these numbers are not real, we're going to call the square root of a negative number an imaginary number. From imaginary numbers, we can build a new number system that we're going to call complex numbers. A complex number is any number in the form of a plus bi, where a and b are themselves real numbers. A is referred to as the real part, and b, since that is being multiplied to I, we're going to call the imaginary part. Now, a couple of interesting facts about complex numbers is first, all imaginary numbers in the form of bi are going to be what we call pure imaginary. And numbers in the form of bi are complex numbers because they can be written in the form of a plus bi, where a equals 0. Also, all real numbers are actually complex numbers. It's the same way as how all integers are rational numbers. All rational numbers are real. Well, it turns out all real numbers are also complex. And that's because for any real number a can be written as a plus 0i, where a itself is the real part and 0 would be the imaginary part. When it comes to simplifying complex numbers, we want to write complex numbers in what we're going to call the standard form. The form a plus bi, which we've seen in the definition of a complex number, is referred to as the standard form of a complex number. And whenever we're trying to simplify expressions or perform operations with complex numbers, we want our answer written in the standard form of a complex number. Now we're going to evaluate each expression. Remember, when we're evaluating each expression, our answer should be in the standard form of a complex number. First, let's take the square root of negative 25. Well, as we discussed 2 slides ago, if we're taking the square root of a negative number, that's going to equal I times the square root of, well, now we'll drop the negative, 25. So the square root of negative 25 equals I times the square root of 25. 25 is a perfect square. The square root of 25 is 5. So the square root of negative 25 equals 5i. One thing I like to point out when writing my complex or imaginary numbers is typically I like to write I in front of the radical. So that way there's no mistake that I is outside of the square root. But if you write I root 25 or root 25i, they both mean the same thing as long as you're just careful to make sure the I is not inside the radical. In the next example, we'll take the square root of negative 75. Because we're taking the square root of a negative number, the square root of negative 75 is going to equal I times the square root of positive 75. 75 is not a perfect square, but 75 does have a factor that is a perfect square, which is 25. And the other factor would be 3. So I times the square root of 75 would equal I times the square root of 25 times the square root of 3. Square root of 25 is 5. Square root of 3 will just stay square root of 3. So the square root of negative 75 equals 5i root 3 or 5 root 3i, depending on where you want to put the I. Now we're going to evaluate the square root of negative 36 plus the square root of negative 49. Following our order of operations, first we have to take the square roots. Well, the square root of negative 36 we know is going to involve an I because we're taking the square root of a negative number. And the square root of 36 is 6. So the square root of negative 36 is 6i. Square root of negative 49, well, the square root of 49 is 7. And because we're taking the square root of a negative number, we would have to have I. So the square root of negative 49 is 7i. When we add imaginary or complex numbers, it's just like collecting like terms. So if we think of I as a variable, 6i plus 7i, well, we would add the coefficients. 6 plus 7 is 13, and we'd bring the I at the end. So the square root of negative 36 plus the square root of negative 49 equals 13i. Now for the next example, we're going to evaluate 3 plus 2i plus 4 minus 5i. The big rule of the parentheses is to tell us that 3 plus 2i is one complex number, while 4 minus 5i is another complex number. When it comes to addition and subtraction, it's just like collecting like terms. We're treating I as if it's a variable and collecting accordingly. So in the first part, do we need the parentheses around the 3 plus 2i? Well, not for the simplification, so let's drop them. And in the second parentheses, we don't need them either because there's nothing to distribute. So we'll just write down the 4 minus 5i. Now we'll collect our like terms. 3 and 4 are non-I terms, so we can add them together. We get 7. 2i, negative 5i are I terms. Add them together, and we get negative 3i. So 3 plus 2i plus 4 minus 5i equals 7 minus 3i. Next, we'll subtract the two complex numbers, 4 minus 2i and negative 3 plus 5i. In the first set of parentheses, there's nothing to distribute, so we can go ahead and drop those parentheses. But in the second set, we have to distribute in the negative 1 before we drop them. So after we distribute negative 1, we would have plus 3 minus 5i. And just like before, we'll collect our like terms. 4 plus 3 is 7, negative 2i minus 5i, negative 7i. So 4 minus 2i minus negative 3 plus 5i equals 7 minus 7i. In the next few examples, we're going to take a look at multiplication. First, we'll multiply 2i with 4 plus 6i. Well, just like in past problems, we're going to use the distributive property. We'll take the expression 2i, and we're going to distribute that into the 4 and the 6i. 2i times 4i, well, 2 times 4 is 8, and we'll have the I there. 2i times 6i, 2 times 6 is 12, I times I is I squared. Now, even though we did perform the multiplication, our answer is currently not in standard form. Recall, standard form is the a plus bi form, which I have written here at the top. Notice there's no I squared in the standard form. So when we evaluate our expressions, we do not want an I squared. So how do we handle the I squared? Well, recall from the definition of I, we explicitly stated that I squared equals negative 1, because we're defining I to be a square root of negative 1, more specifically the principal square root. So to continue writing this product in standard form, we're going to replace the I squared with negative 1. Now that I squared is replaced with negative 1, we would have 8i, well, 12 times negative 1 is negative 12. So we have 8i minus 12, and just rewrite the order of the terms, and we get negative 12 plus 8i. It's very important that you remember that I squared is negative 1. I squared does pop up quite a bit when we're multiplying complex numbers, and using the fact that I squared equals negative 1 is how we're going to write that product into standard form. In the next example, we're going to multiply 2 plus I with 3 minus 3i. We can think of this as multiplying binomials, which means we're going to FOIL. So under foiling, we would do the first. 2 times 3 is 6. Outer, 2 times negative 3i is negative 6i. Inner, I times 3 is 3i. And then last, I times negative 3i is negative 3i squared. Now, currently, we are still not in standard form. Before collecting any like terms, we need to replace that I squared with a negative 1. Now, let's collect our like terms. First, the 6 plus negative 3 times negative 1. 3 times negative 3 times negative 1 is positive 3. 6 plus positive 3 is positive 9. Then we'll combine the i's. Negative 6i plus 3i is minus 3i. So 2 plus I times 3 minus 3i is 9 minus 3i. For the 4 minus 3i squared, we can think of it as squaring a binomial. And we do have a special multiplication rule for it, where if we have a plus b squared, that equals a squared plus 2ab plus b squared. So if we apply that special formula, a would be 4, so we would have 4 squared, plus 2 times 4, again is a. Our b is negative 3i plus negative 3i squared. Now do a little bit of cleanup. 4 squared is 16. 2 times 4 is 8 times negative 3 is negative 24. And don't forget the I. And negative 3i squared. Well, negative 3 times negative 3 is positive 9. I times I is I squared. Now we can replace the I squared with negative 1. And then we can simplify and combine the non-I terms. And we have 4 minus 3i squared is 7 minus 24i. Now, another way we could also handle the 4 minus 3i squared is you could write it as 4 minus 3i times 4 minus 3i, and then proceed to FOIL. But that's up to you. Now we're going to explore various powers of I. We focus on the powers of I on the right. Let's focus on the powers of I here on the left, where we have I to the first, I to the second, I to the third, so on and so forth. If we take a look at I to the first, well, anything raised to the first power is itself. So I to the first equals I squared, we know from definition, is negative 1. Now we're getting into some higher powers of I, specifically I to the third. Well, I to the third is the same as I squared times I. Now we already know what I squared is. We know I squared is negative 1, and I is just I. Well, negative 1 times I is negative I. So I cubed is negative I. Now what about I to the fourth? Well, using our exponent properties, I to the fourth would be the same as I squared times I squared. Well, I squared, we already know is negative 1. And negative 1 times negative 1 is positive 1. Let's keep going with I to the fifth, I to the sixth, I to the seventh, and I to the eighth, and see if we can establish a pattern. If we take a look at I to the fifth, that's the same as I to the fourth times I. And we've already determined that I to the fourth is 1. So we would have 1 times I, and anything times 1 is itself. So I to the fifth is the same as I. If we take a look at I to the sixth using the same idea, I to the sixth is the same as I to the fourth times I squared. Well, I to the fourth we've already determined to be 1. I squared we've already determined to be negative 1. 1 times negative 1 is negative 1. Going to I to the seventh, that's the same as I to the fourth times I cubed, both of which we've already figured out the values for. I to the fourth, the same as 1. I cubed, we've already found to be negative I. 1 times negative I would just be negative I. So I to the seventh is negative I. And lastly, I to the eighth is I to the fourth times I to the fourth. I to the fourth is 1, and 1 times 1 is 1. If we take a look, we can see a pattern starting to emerge. Pattern is I, negative 1, negative I, 1. And then after the fourth power, we cycle the pattern again. I, negative 1, negative I, 1. What this tells us is our pattern repeats in a cycle of 4. I, negative 1, negative I, 1, and then the cycle repeats. I, negative 1, negative I, 1, and it's going to keep going forever. So if I wanted to figure out I to the 9th, I to the 10th, I to the 11th, I to the 12th, well, those would be I, negative 1, negative I, and 1, respectively. Now we're going to take a look at each of these examples here on the right, where we have I to the 124 starting off. Now, I to the 124 means we're multiplying I to itself 124 times. And that can be a bit cumbersome to write. But thanks to our pattern, we can make this a little easier. If we do 4 divided by 124, we get 31. So I to the 124 is the same as I to the 4 times 31. This means to get to the 124th power of I have to go through this 1, negative I, 1 pattern exactly 31 times. Well, since I'm completing this pattern exactly 31 times, and the last number in our pattern is 1, I'm going to get that I to the 4 times 31 equals 1, which means I to the 124 is 1. Now I'm going to do the same thing for I to the 603. Because my pattern is a length of 4, I'm going to divide 603 by 4. And when we divide 603 by 4, we get 150 with a remainder of 3. What that means is I'm going to complete the pattern 150 times, but I have 3 left over. So I have to go into a partial cycle where I'm 3 slots into that pattern. I to the 603 is going to be the same as I to the 3rd, because once when I finish the first 150 cycles, the full cycles of 4, I'm going to wind up at 1. Well, going to 601, 602, 603, I'm not finishing a full cycle, so I still have 3 numbers into my cycle to account for. So I to the 3rd is going to be negative I. I to the 782, we're going to divide the 782 by 4 to see how many full cycles we go. And when we do, we get 195 with a remainder of 2. That means we're going to complete 195 full cycles of our pattern. We're only going to go 2 of the way in to the next cycle. Since after every 4, we wind up at 1, our I to the 782 would just be the same as I squared. And I squared is negative 1. Lastly, I to the 555, divide the 555 by 4. And when we do, we get 138 with a remainder of 3. So just like before, we complete 138 full cycles of 4, landing us at 1. But because the remainder is 3, we have to go 3 into the next cycle, which means I to the 555 is I cubed, and I cubed is negative I. In the last section, we did not like having radicals in the denominator of our expressions. The same is going to hold true for the number I. We do not want to have I in the denominator of expressions. The idea of getting rid of the I in the denominator is similar to what we did with rationalizing the denominator. Oftentimes, we're going to work with the complex conjugate. The complex conjugate of a number a plus bi is a minus bi. Just like with conjugates before in the previous section, if I have a number, its conjugate, I just switch the sign. So if I see a plus bi, its conjugate is a minus bi. If I see a minus bi, switch the sign to a plus bi. That's how you get the conjugate. Now let's take a look at a few examples where we're going to evaluate each expression. And remember, when we evaluate these expressions, we want our answer at the end in the standard form of complex numbers, which is the a plus bi form. So starting off with the first example, our denominator is a complex number. More specifically, it's pure imaginary. When our denominators are pure imaginary, the only thing we have to focus on is getting rid of the I. The way we're going to do that is we're going to multiply top and bottom of our expression by I. In the numerator, when we distribute in the I, we get 10I minus 2I squared. And in the denominator, 2I times I would be 2I squared. Since I squared is negative 1, 10I minus 2 times negative 1 in the numerator, all over 2 times negative 1 in the denominator. Rewriting the numerator, negative 2 times negative 1 is positive 2. We do like having the imaginary part behind the real part. So we'll rewrite the order as 2 plus 10I, and 2 times negative 1 is negative 2. So we were able to get rid of the I in the denominator, and we were able to rationalize our denominator. But we still want it in the standard form, the clear a plus bi form. So we'll divide each term in our numerator by our denominator. So we have 2 over negative 2 plus 10 over negative 2i. And if we simplify, we get negative 1 minus 5i. In the next problem, to rationalize, we'll multiply top and bottom by I, just like what we did before. When we distribute into the numerator, we get 5i plus 3i squared. In the denominator, we get 4 times I squared. As always, replace the I squareds with negative 1. So we get 5i plus 3 times negative 1 over 4 times negative 1. Simplify a little farther. 3 times negative 1 is negative 3. And we'll put the plus 5i in the end. 4 times negative 1 is negative 4. And just like before, we're going to divide each term in the numerator by the denominator and then clean it up. Negative 3 over negative 4 is positive 3 over 4. 5 over negative 4 is negative 5 over 4. So 5 plus 3i over 4i is equal to 3/4 minus 5/4 I. In the next problem, we're going to evaluate 3i over 1 minus 2i. Because our denominators are not pure imaginary numbers, we are going to have to use complex conjugates to help simplify. What is the complex conjugate of 1 minus 2i? Well, remember with complex conjugates, we switch the operation in the middle. So we change the minus to the plus, and the complex conjugate of 1 minus 2i is 1 plus 2i. And we're going to multiply top and bottom by 1 plus 2i. In the numerator, we can simplify by distributing in the 3i, and we get 3i plus 6i squared. Now in the denominator, we can use the same special multiplication rule we did in the previous section. If we have a plus b times a minus b, that is equal to a squared minus b squared. As an alternative, you could also FOIL, but using the special formula, we get 1 minus 4i squared. We'll do some cleaning up. Replace our i's with negative 1. In the numerator, 6 times negative 1 is negative 6, and we'll put the plus 3i behind. In the denominator, 1 minus 4 times negative 1 is positive 5. So we have rationalized the denominator. Now we just want to write it in standard form and see if there's any simplification we can do. Dividing each term in the numerator by 5, and we get that 3i over 1 minus 2i is negative 6 over 5 plus 3 over 5i. And in our next example, we have 4 minus 2i over 2 plus 4i. Since our denominator is not a pure imaginary number, we're going to have to use complex conjugates to simplify. The complex conjugate of 2 plus 4i is 2 minus 4i. In the denominator, using the special multiplication rule I've listed at the top, we get 4 minus 16i squared. In the numerator, we are going to have to FOIL. And when we do, we get 8 minus 16i minus 4i plus 8i squared. Replace the I squareds with negative 1. Then we can simplify. 8 plus 8 times negative 1. Well, those are going to cancel because that sums to 0. Negative 16i minus 4i is negative 20i. Denominator, 4 minus 16 times negative 1 is 20. And if we simplify, we get negative I. So here, 4 minus 2i over 2 plus 4i is equal to the pure imaginary number, negative I. Now, how do we organize complex numbers? The way we organize real numbers is on a number line. The way we're going to organize complex numbers is using something called the complex plane. Now, the complex plane is just a Cartesian plane. But in the Cartesian plane, we label the horizontal axis the real axis and the vertical axis the imaginary axis. What this allows us to do is it takes any complex number a plus bi. We can represent that as a point AB. So A, the real part, would be the first component of our point. B, our imaginary part, would be the y component of our point. And this point AB, we would plot on the complex plane. Now we're going to take a look at a few examples of us plotting complex numbers on the complex plane. The x-axis is going to be referred to as the real axis, as we stated before. And the y-axis, we're going to refer to as the imaginary axis. Now, each complex number we can associate with a point. So 2 plus 3i, we'll associate with the point 2, 3, since the real part is 2 and the imaginary part is 3. Where would we put 2, 3 on this plane? 2, 3 would go right there. Now, what about negative 4i? Where would that go in the complex plane? Well, this is a pure imaginary number. Remember, pure imaginary numbers can be written as 0 plus that number, or in this case, 0 minus 4i. So our real part is 0, our imaginary part is negative 4. So 0, negative 4, we would plot down there. Next up, negative 2 plus 5i. Negative 2 plus 5i would be associated to the point negative 2, 1. The real part is negative 2. The imaginary part is 1. Since we don't see a coefficient of I, we assume the coefficient is 1. So where would we put negative 2, 1 on our plane? Negative 2, 1 is located there. Lastly, 5. Now 5 is a real number. But remember, all real numbers are also complex numbers because we can add 0i to the end of them. So the number 5 corresponds to the point 5, 0, since the real part is 5 and the imaginary part is 0. And where would the point 5, 0 go on our complex plane? It'll go right there.